All right. Well, I just realized I screwed up royally. I didn't send out the invitations until like just a second ago. So, sorry about that. It's just, coming back from the vacation and Christmas, I guess I just forgot. But you have them now. So why don't we wait a minute for everyone else to catch up and then we'll get started. By the way, anyway, so what we're going to do today first is look at our second, or actually our sample midterm. And we're going to go through it and go through all these problems. And when we're done, we'll be ready to take the first midterm. Okay, so hold on one second. All right, yes, more people are coming. Good, good, good. Yeah, so whoever just got here, I was apologizing for forgetting about that invitation. It's just that, everything during the school year, everything is so rigid and, it's easy to remember things. And now we're on kind of on Christmas break and it's easy to forget. So I'll make sure that doesn't happen again. All right, so let's take a quick peek at this. No, 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 no. The real midterm will be done by you at home, um, not during class time. Okay, yeah. So no, we're not doing any kind of in class. No exams will be done during the actual class. Yeah. So in other words, when we're done reviewing here, I'll just post the actual exam, and then you'll do it at home, and then you'll send it back to me. The way you're also sending back the solutions to the chapter 3 and 5 problem sets, which basically means I don't see what else you can do. You can either take pictures of it with your camera phone, or else if you have an actual scanner, if you have a printer in your house, it probably has scanning capabilities, and you can do that too. You can scan it into a PDF file, but if not, that's okay. You can take pictures with your phone. The only thing you have to do is before you send it to me, look at it yourself and see if you can read it. Because if you can't read it, I can't read it. Most of the time, it's been my experience that the quality is usually pretty good, but you got to be careful, especially if there's a lot of glare. If you're writing in pencil, it can come out very faint. If it's really small, things like that can make it very difficult to read properly. So, just be a little careful. That's all. All right. It looks like just about everybody's here. So, yes. As far as that goes, yes, that's a good question. We have a question about whether or not we should show the work. The thing about showing the work is you should ideally show the work because number one, it'll help you prevent yourself from making mistakes. But also, if you have a wrong answer, but I see what you've done, that makes it a lot easier for me to give you partial credits. So think of it as like an insurance policy. Let's say you get through the whole problem and at the end you make a sign error or something, then I can see that and I can give you just about all the points. Whereas if you just write down a wrong answer, there's not a whole lot I can do about that. So now you don't have to go berserk. Just show the basic steps. How did you get your results? And that's all that I really need. It's not necessary, but I think it's an excellent idea. Let's put it that way. All right. So I think, yeah, we might be waiting for one more person. So hopefully, yeah. All right. Well, we'll just start now then. And all right. So if you look at this document, you'll see now, keep in mind, this document was written for a time when we actually did our learning in a physical school instead of online. So this part was intended to be a quick review of all the terminology that we've covered in chapters 3 and 5. So it's not quite as useful now since you'll be doing this at home anyway, but it is, I think, helpful to organize your thinking about what we've actually done and to make sure you understand what we've done. And so I don't know, I kind of like to have it all organized in one place like this. So if you go through here and you see something that you don't recognize, you'll have an opportunity to go investigate it. Everything in here was taken directly from the slides. And they're all, of course, on Moodle, which, oh, you know what that reminds me too. Let me go back and get Moodle open. So yeah, I had this conversation with the school about the videos. You know, I thought, oh, what the heck, you know, because I have Blackboard at other schools, and it seems to allow you to put videos on it, but there's something about Moodle that apparently it's just not set up for that kind of thing. So I had a couple of them up there, and I just took them out because apparently they're just going to suck up all the space. So what I think what I'd like to do is, even though you can certainly go to my YouTube account and look at the videos, which you've probably been doing anyway. But what I think I would like to do in addition, just to make things a little bit easier, here they are. Now, there's a playlist here. They're organized into a playlist. You'll obviously see different playlists than I see, but you should, well, actually, no, you won't. You'll be seeing all of these too, I think. I don't really care. But yeah, I've got all this music in here too, but this is obviously what you're looking for. Oh yeah, there we go. Okay. So all the videos are stored in here in this playlist. And they're of course in chronological order. But what I was thinking that I might do is actually take the links and put them directly into Moodle, which can be done. I don't know, it might be a little quicker that way. This way you could click it on and just watch it directly. So I'll work on that. But one thing apparently that we can't really do is put the videos directly into the Moodle because it just doesn't have that capability. So, which is kind of unfortunate, but that's just the way it's set up. All right. But having said all that, you have access to all the slides right here. They're all right here where you can just download them and watch them or not. You don't have to watch them if you don't need to. The slides are what you really need to study from more than anything else. And so anyway, so in the meantime, I just want to remind you that the first midterm is based exclusively on chapters 3 and 5. Okay, our introduction to statistics, summary measures, and probability theory will all be on this test. But everything here is something we've already covered. There's no surprises in here. Everything is just exactly what we've been doing. So now this section, these are the fill-in questions. These usually require only, let's say, a sentence or two, or in some cases, a single word or a single number. Now, when we do these in the classroom, it's been my experience that for whatever reason, people tend to lose a lot of points in this section. Maybe they didn't realize that this was going to be there, but since you're going to do this at home, these questions should not be difficult because you'll have access to all your notes. But still, it's important to go through them all so that to make sure that we understand what we're doing. All right, so why don't we start with these so-called fill-in questions. Now here you're asked to write down the axioms of probability. Okay, now on the actual test, I think it only asks for one or two of them. If that happens, then you can just do one or two. You're not required to put all three of them in unless it specifically asks for them. All right, so in other words, you're never required to give more information than it asks for. And remember, in this section, a lot of these are meant to have very short answers. And like I said, it may be that the answer itself is a single word or a single number. So in other words, don't feel like you have to write an essay for each of these questions. Okay, so here, what's the first axiom? I'm just going to write them all down. The probability, and you can do this in English if you can, not always. It's not always possible to do this exclusively in English, but the probability of any event, A, is non-negative. And what that basically just means is that it's not negative. In other words, it could be zero, but it can't be negative. That's all that that word means, non-negative. In other words, positive means that it's not zero, but it can be zero. So therefore we call it non-negatives, which simply means either positive or zero. Axiom 2, the probability of the entire sample space. Actually, let me make this just a little bit bigger here, because I know that what you're seeing on your screen is probably a little bit smaller than what I'm seeing here. So let me make that just a little bigger. The probability of the entire sample space is 1. In other words, that's just another way of saying that the probability of S equals 1. Now, axioms 1 and 2 combined imply that all probabilities are bounded between 0 and 1. It doesn't actually say it that way, but if you combine the two of them logically, that's the same thing as saying that all probabilities must fall between 0 and 1. And just as a side note, this is not part of the question. I just want to remind you that a probability, or what I should say is an impossible event, has a probability of 0. A certain event has a probability of 1. Again, you do not need to put this in here to answer this question. I just wanted to remind you of that. Now, the third one is a little challenging. For any collection of mutually exclusive, which is also known as disjoint, by the way. That's just another way of referring to mutually exclusive events. Okay, now remember, so this just simply means they're all mutually exclusive. None of them has any elements in common. We have the following claim, that the probability of their union can be written as the sum of the individual probabilities. Okay, so in English, the probability of the union of these events equals the sum of the individual probabilities. And in fact, you'll recognize this as the general version of the simplified addition rule. In other words, the simplified addition rule refers to the case where we have two mutually exclusive events. And we know that for that, we simply add up the two individual probabilities. Here, this can be extended to any number of events as long as they're all mutually exclusive. Now, remember, the axioms themselves are simply statements that we do not attempt to prove. This is what we're assuming when we start developing a system of logic like probability theory. There's no reason why we couldn't have defined probabilities to be negative, but it doesn't make any intuitive sense. So just to keep things as simple as possible, we're going to assume right up front that no probabilities can be negative and that these other properties hold as well. All right, now what conditions must be met for two events to be independent? Now there's two of them. They must both be true. One is not good enough. Now, by the way, I would resist the temptation to write this in English. It's a little more challenging, in my opinion. You can attempt to write this in English, but as long as you have symbols, I mean, that's where math really shines. I mean, it really expresses a lot of information in a very compact way. It's just, this is good enough. If you try to explain it in English, what you're trying to get across is the idea that the outcome of one event does not affect the outcome of the other event. Okay, and it's a little bit, I don't know. It just seems to me that writing it like this is a little simpler, but if you want to write it in English, you would end up explaining it something like this. The outcome of each event has no influence on the other event. Oh, for God's sake. I guess that, you see what I mean? It's very awkward to do this in English. No matter what you do, there's some vagueness that gets built into your sentences, but this is very clear and compact. Okay, now, correlation coefficient. What range of possible values does it have? Between -1 and 1, and that's it, bottom line. It can never fall outside that range because of the way it's defined. Okay, that was done intentionally because it's convenient to think about these values as being somewhere between 0 and 1 on the positive or negative side. By the way, when we're done here, I'm going to post a copy of these answers onto Moodle. So you don't have to feel like you have to write down every single word. You'll have your own copy of this. And of course, the video, you can watch it as well. All right, so if a sample is negatively skewed, now you might remember, we went through this in chapter 3. We had a graph that looks something like this. A series of tall bars. With maybe a few other observations down here, for example. And you can imagine that if you put a curve on this, it would look something like that. In other words, it has a long left tail. And this results when the mean is less than the median, which is in turn less than the mode. This is what causes, or this results in what we call negatively skewed, or a negatively skewed distribution. This is the actual meaning of negative skew. Okay. So, what is the relationship between an event and the sample space? Very simply, we can express this in terms of set theory. An event is a subset of the sample space. So you should probably write it that way because it is very precise and very specific. And of course, you remember what a subset means. It means all the elements in the subset belong to the bigger set, or in this case, the sample space. Now, what must be true for two events to be complements? Again, there's two conditions that have to be true. This one can be written in a few different ways, though. So, for example, I could write it in terms of, for example, I could write it as A union B equals the entire sample space, and their intersection is the empty set. But if you choose to do it, there's another way you could do this. You could also write the probability of A union B is 1, and the probability of A intersect B is 0. And again, it has to be both. One is not good enough. Either one of those will get you the same results. They both mean the same thing. Okay. All right. All right, let's try this one. Number 7, if A and B are mutually exclusive events, what is the probability that both of them will occur? 0, because they can't both be true. It's like, imagine I said to you, what's the probability of picking a card from a deck? And it's both red and black. Well, the probability of that happening is 0, of course. All right, well, that was nice and easy. How about this one? When is the simplified multiplication rule used? When the events are independent. Okay, not mutually exclusive like with the simplified addition rule, independent. All right. Now here we have an experiment consists of choosing a single card from a deck. A is the event that the card is red. The complement of A, which we'll write as A complement, would be the card is black. How do you know that? Because, I'll just mention this, this is again not required for the answer, but I'll put this in brackets here. We know this because of two things. All cards must be either red or black. And 2, no card can be both red and black. Okay, so in other words, this is the explanation. Why is this true? Because of the way the deck is constructed. Half the cards are red, half are black. They're all one or the other, but no card can be both. All right, and when is this simplified? Here it is, simplified addition rule. When the events are mutually exclusive, that's when we use it. No other time. All right, now we get to do some problems. All right, so how do we do this? Well, first of all, the mean is pretty straightforward. What are you doing here? You are simply adding up all the elements and dividing by the sample size, which in this case, of course, is 6. So I'll make a note here that n equals 6. And also, let's note that this is a sample, not a population. That's a huge deal. Okay, because at least some of the results will be different depending whether it's a sample or a population. So here we have X bar. So we'll just literally add them up. And that's 12 over 6, which is 2. Well, that was pretty easy. Very nice. All right, now how about the median? Now, of course, don't forget to sort them. The sorted sample is -1, 0, 1, 3, 4, 5. Okay, once that's been established, the median with an even number of values. The median is the average of the two elements in the center. Okay. Which are, of course, okay, 1 and 3. So therefore, this equals, as you can plainly see, 1 plus 3 over 2, which is just 2. 4 halves are 2. Okay, so right now, as it turns out, it has the same mean and median, which happens sometimes. It's not a common thing, but it happens. All right, C. Now, again, we need for the mode the sorted sample. And again, this is something you should write down. I mean, this step is not absolutely necessary, but I think it's an excellent idea. And you notice when you look at it this way, since there are no repeated elements, there is no mode. Okay, no mode. It happens. There's no guarantee that there'll be a mode. All right, so don't be shocked when that happens. Now, the third quartile. Once again, we need the sorted sample. So the index or position for the third quartile is n3, n plus 1 over 4, which equals 3 times 6. Remember, there's 6 elements, plus 1 over 4. 3 times 7 over 4, 21 fourths, which is 5.25. Yes, 5.25. Now, of course, there is no 5.25 element. Of course, no, there wouldn't be. So what do we do about it? We must interpolate between the 5th and sixth elements. No, not this case. That's a good question. Because it applies equally to samples or populations, this is one time where you could just as easily put a lowercase n or an uppercase n. That is kind of an awkward feature of this formula. You know, if for whatever reason, they do not typically make a distinction between the two. If you want, I mean, we can change it to n's, but it's not going to affect anything. So why don't we do that? Let's change this to a lowercase n, just to make it completely consistent. But for whatever reason in the book, they just use the capital N for all the cases. And I don't know why, they just do. Sometimes you get inconsistencies. All right, but we have to interpolate between the fifth and sixth elements. Why? Because whatever we're looking for is somewhere between elements number 5 and 6. Now, that means these two. Okay, so just to make that crystal clear. So we need to find, well, here's how it works. We need to start with element number 5, or this, let's say the fifth element, which is 4, and then add 25% or 0.25 of the distance between elements 5 and 6. Okay, so in other words, we're going to have 4 plus 0.25. Now, the two elements we need next, element 6 is a 5, this is 4. So in other words, you can think of it as somewhere between 4 and 5 is what we're looking for. And that number is 4 plus 0.25 times 1, 4.25. So think of this as our third quartile. It's sort of in between. We know it's not either element by itself, but we do know that it's in between.
Professor Anderson, why wouldn't it be 0.75?
Wait a minute. It's 21 over 4. See, now you got me thinking here. 21 over 4 is 5.25. Yeah, no, it's, in other words, it's 25% of the distance between elements 5 and 6.
Got it. I thought it was like 75.
No, you know why? Because of this formula, it gives us an index of 5.25.
Okay.
And so basically think of that as 25% of the distance between elements 5 and 6.
Okay.
All right. Now, the values of those elements are 4 and 5. Okay. This number 4, in fact, let me add this here. This is element number 5. Just to make it even more, let me just fix up my little diagram here. And then this is element number 6. So we have to be very careful to not confuse the indexes with the actual values in the sample. Okay, so in other words, the 5 and the 6 are indexes. These are the actual values in the sample. So it's like you have a map, say you have a treasure map, and it says, listen, there's 2 trees on the property. Walk 25% of the distance between this 4th tree and this 5th tree, and you'll find your treasure. In fact, if I move it out here somewhere, it'll look even more realistic. Does that work? Yeah, I guess so. So anyway, so that's what we're aiming for. When the dust settles, this is the answer that we're actually looking for, right there.
Got it. Thank you.
Okay. Now the range, by comparison, is such a breeze. We love the range because it's equal to, well, first let's go back and revisit our sorted sample. Okay, let's go grab that again. Okay, I don't know what that is. Obviously, I hit the wrong button somewhere along the way. Okay, so the range equals maximum minus minimum, which is 5 minus minus 1, which is just equal as 6, and that's all there is to it. Okay, now interquartile range is another name for Q3 minus Q1. We already know Q3, but now unfortunately we have to do number 1 to find out this answer. So we're going to do the same thing that we did up here, except we're going to look at the first quartile, and that would simply be not 3n plus 1 over 4, but just plain n, which gives us 7/4. And this one actually is 1.75. So we need something that's 25. We need something, the element that is 75% of the distance between elements number 1 and number 2. Okay. And those elements are, if you look at the sorted sample again, are -1 and 0. All right, so let's do the same thing we did before. Let's draw out a little graph. Well, actually, here I did the calculator first, and then I drew the graph. So we start the first element, which is -1, and then add 0.75 times the distance between elements number 1 and 2. Okay, so in other words, what we're doing is putting -1 plus 75% of the difference between, now remember, the next element is 0. So it's 0 minus -1, -1 plus 0.75 times +1, so it's -0.25. All right, now let's draw our graph and see why this is happening. I'm going to basically steal this one because I like it so much. Element number 1 is -1. Element number 2 is 0. And Q1 is therefore. Now here I've got to fix the picture a little bit though, because you can see it's meant to be much closer to 2 than 1. So let me fix this. Yeah, that looks about right. So we are aiming for the opposite of what we had before, 75% of the distance between these two, where the rest is 25%. So now what we know is that Q3, which we had earlier, turned out to be 4.25. Q1 is just found, which is negative 0.25. So since the interquartile range is the difference between them, all we have to do is subtract one from the other. Okay, and so we end up with 4.25 minus negative 0.25, 4.50. So all that work just to find out that the interquartile range is 4.50. It's a bit of a headache, but it's done. Wow. All right, so all the steps are here. So you can look at these when we're done if you missed something. Now the variance, now remember, we went out of our way to notice in the beginning that this is a sample. So therefore, we're going to use this formula. So remember, the rule of thumb is that Greek letters are used for populations, Roman letters are used for samples. And you also recall from earlier that X bar is 2 and N is 6. So now we just need the original data. Now, this one does not require to be sorted. The order, in an example, for an application like this, the order is completely irrelevant. Let's go get those numbers back, just so we can see what we're doing. Now, this one takes up a lot of space. So if you're writing this down on a piece of paper, leave a lot of room. It's not likely that you'll fit it all in. You'll probably have to spill over to the next line. So you have to go through them one at a time. So we start with the negative 1. In each case, we're going to subtract the mean of 2, square it, and then we go to the second one, 0. Do the same thing, subtract 2 and square it. Go to x3, which is 5. Here's x4. x5 is 1. Ooh, it looks like I'm going to make it here. And then we have 4. Okay. Now we just have to evaluate this, but before we do that, probably our best bet is to figure out what's going on in these parentheses. Okay. I thought I saw the chat going off, but I guess not. All right, so let's figure out what's in the parentheses. I'm just cleaning it up a little bit. All right, so with that being done, now we can go ahead and figure out what these square terms are. 9 plus 4. Of course, they'll all be positive. Whoops. All right, so the sum in the numerator, that is 28. And our final result is 5.6. Ooh, another gruesome problem. Yes, but as long as you're careful, there's no reason why you should get it wrong. Now, this is a perfect example of why you should show your work, because you can see how easy it would be to make a mistake here. If you left off one of these squares, for example, you'd have the wrong answer, and if there's no work, I can't tell what happened and just lose all the points. So by writing out all these steps, you're guaranteeing yourself, if you've done it correctly, you should get at least part of the credit. Like I said, it's like an insurance policy. Okay, since you're doing this at home without any time pressure, there's really no reason why you should leave out these steps. Okay. Um, unless, I don't know, unless you're taking a bunch of other classes, which you probably aren't. Anyway, so now the nice thing about this, of course, is that when that's done, the standard deviation is a breeze. What do you have to do? You literally just take the square root the square root of 5.6 is approximately 2.366. And you're done. It's that simple. The coefficient of variation is also easy once we've already done all this work, because remember, all it is the standard deviation over the mean times 100. And that's going to give us approximately 118.3%. Okay. All right, good. So far, so good. Is anyone having any problems? Do you need to ask any questions? Okay, everybody's here. Very good. All right, if not, we'll just carry on. Now, look at this chart. We've bought a stock. We held it for 50 trading days. And what this table represents is what rate of return you earned on a daily basis over those 50 days. Now, we don't have the original data. What we do have, though, is the frequency, what's called a frequency distribution, which says 10 of those days we lost 2%. 12 of those days we lost 1%. 14 of those days we broke even. 8 of those days we made 1%, and 6% of those days we made 2%. Now, it says, what is the average daily return during this period? Well, it should be pretty clear, although it doesn't actually say this, that here we're looking for a weighted average because many of the observations are repeated, and also because you don't actually have the original numbers. So you actually can't use any other formula except for this weighted average. So let's just say that this is a sample. It doesn't, now this is one of those formulas where it really doesn't matter if it's a sample or a population. If it doesn't explicitly say so, you can just pick one or the other. I won't give you any points off. Let's just assume that this is a sample. To recall, the formula here asks us to take all the weights. These are the weights, by the way, these frequencies, multiplied by the actual values of these returns. And then in the denominator, you're simply adding up the weights. So think of this as x1, x2, x3, x4, and x5. And these are the weights. The frequencies are always the weights. We're not so much interested in that. That just tells me how often this happened. What I'm really analyzing is the returns. Therefore, those are the x's. Okay, now what I'm going to do is split the screen so I can see what I'm doing. Oh no, almost. Let's get here we go. All right, I want to be able to fill in the formula and yet have you still be able to see the numbers. Okay, so let's do it down here. I'll run out of room otherwise. So remember, go to the first row, weight 1 times x1. By the way, this is not necessary, but I personally think it's easier to deal with percentages by turning them into decimals. I just think that it's easier to avoid mistakes. That's what I'm going to do. You can leave these as whole numbers, but I don't know. I just find it easier to do it this way. Oh, you know what? I can tell already I'm going to run out of space. So let me start that all over again. All right. So yeah, you see what I'm doing here? I'm converting -2% into -0.02. You can always convert it back to the percentage format if you want to, but I like, oh God. All right, better this way. And then in the denominator, of course, you're simply adding up those frequencies, which do in fact add up to 50. All right, so if you see how this was done, then all you really have to do is be careful. Okay, so in other words, what exactly are these numbers? First of all, we're multiplying 10 times -0.02. Then we've got 12 times -0.01, -0.12, the third term is clearly 0. That's always nice. The next term is 0.08. And then the last term is 0.12. All of that is divided by 50. Whoops. Okay, so we go through, add these up. That's -0.12 over 50, which is -0.0024. And in order to convert that back into a percentage, you just multiply it by 100. So if you want to write it as a percentage now, multiply that by 100, and you get -0.24%. Which means on an average day, I'm losing 0.25%. That's not very good. Hopefully that will turn around in the future. By the way, here's a little interesting fun side fact. You know that the way to convert into decimals, as you've seen, is to multiply by 100. Supposedly the symbol for percentage itself, and of course it's hard, often we end up using these symbols and it's easy to forget where they came from. This supposedly is just a rearrangement of 1, 0, 0. Okay, you see 0, 1, 0, 0. That's supposedly where the symbol comes from. It's like, it's hard to be sure if that's true or not, but that's what's supposedly. It's just like the symbol for the US dollar. Surprisingly enough, nobody actually knows the actual origin of that symbol. There's a lot of theories, but nobody is sure about where it actually comes from. It's just one of those weird things, and it's not a very old symbol either, and yet somehow its origins have been lost in the mists of time. So you never know with symbols. They all have potentially at least interesting origins. Anyway, so let's go on to the next one. Ooh, yeah, here we go. This is the one that's going to take a while. Yes, because we have a lot of calculations to do here. So why don't we start at the beginning? We need to calculate the sample mean and sample for both X and Y. This is sample X. This is sample Y. And let me just remind you what this formula looks like. Now, first of all, these are samples. Always notice that first. Are these samples or populations? In a case like this, it matters a great deal because your result will be different if this is a sample compared with a population. So the sample covariance is this. Okay, I think all these terms are pretty familiar, except remember here, this S is actually being used for double duty. S by itself is the sample standard deviation. When you see two subscripts like this, that means it's the sample covariance. I guess nobody could think of another symbol, so they decided to do this. And you notice that there's a mean for both samples. The correlation coefficient in this case so remember now there's a subscript here. This is the sample, this is the standard deviation. Of sample X. And the subscript is only necessary here because we have two of them. In our other cases, we just didn't bother with the subscript because we don't really need it. But here we have to tell them apart because there's two samples. So we'll call the sample standard deviation for X, and this is the standard deviation of sample Y. And of course, this is the sample covariance. Very well. So the first thing you always do in these cases is calculate the sample means. Okay. Oh, and one more detail here. N is 5 in this case. It's not 10, it's 5, because each one has a common sample size of 5. All right, if you add these three numbers up, and divide by 5, you'll see that the sample mean is 2. Okay, the sum in the numerator is 10. And then for Y bar, we go through and add them up. And if you add these up, this is 20 over 5, which is 4. Well, now we apply this really scary formula here, right there. So what I'm going to do, because I'm running out of space, is copy these numbers down below so we can keep track of everything. And a quick reminder, let's just do this. So X bar is 2, Y bar is 4. I'm writing it down again so you can see it away. Oh, and N equals 5. Okay, now we're all set. So I'm going to write over here. Now, almost certainly we're going to run out of space. Don't worry about it. So, but remember, what are we doing here? We start at the top. X1 is -3, and X bar is 2. Here we need Y1, which is 1, and Y bar, which is 4. Oops, hold on. Now, you do not have to write this stuff above the numbers. I'm just putting it here so you can remember what exactly we're doing. All you need is this part down here. Now we go to the next row, X2. Same thing, always subtract X bar from each X, Y bar from each Y. Now Y2 is 5. Okay. For the next row, 4 is X3, and 6 is Y3. Yeah, I figured we'd run out of space. That's right. It should be clear what we're doing anyway. Okay, so we go to row 4. And here Y4 is 7. And then finally, the last row, we have X5 is 7 and Y5 is 1. Now, n-1 would therefore be 4. I'll write it as 5 minus 1. All right, now with that disaster taken care of, what we probably should do now is simplify it. Let's just go through and simplify each set of parentheses. Before we do anything else. I personally think that this reduces the risk of mistakes. If we do it, don't try to do too many steps at once. That's often a sure recipe for disaster. I'm sure you've discovered that yourselves. Now, we can simplify this a little further. This first one, for example, is 15. And we have -2 plus 4 plus 0 minus 15. And that ends up giving us 2 out of 4, which is a half. Oh, man. So that is our sample covariance. Of course, now we're not done because we still need the sample correlation coefficient, which unfortunately requires us to calculate a sample standard deviation for both X and Y. Okay, now we already know how to do that, but we still have to be careful. So let me go grab the numbers again. We're going to need them. Oh, we don't need this anymore. So we already know that, for example, X bar is 2 and Y bar is 4. We have, and just a quick reminder, now when we have 2 of these, we're going to call this SX instead of simply S. All right, that's everything we need. So let's do these sample standard deviations. I'll tell you what, why don't we do these in 2 stages? Let's do the variance first, and then we'll take the square root. How about that? Then we'll go through the x's only for this one. So remember, go through each one, and in each case, subtract x bar, and then you square the result. And then you divide by n minus 1. Okay. Let's simplify. All right, that's going to give us 25 plus 4 plus 4 plus 0 plus 25 over 4. What is that? 58. It's 58 fourths, which is 14.5. That's the variance. Okay, we don't want the variance, do we? No. The square root of that is what we really need, and that's equal to about 3.81, let's say. Okay. So we're not done yet. Sadly enough, we still have to do the standard deviation for y. Oh. All right, so I'll give you a minute to catch up, then we'll do y, and then we'll have our sample correlation coefficient. All right, is everyone done? All right, good. Now I'm going to go back. Yes, I'm going to have to copy these again. This is when in the classroom, we'd have an enormous whiteboard, which is, so nice and easy. This is a little bit of a nuisance, but that's all right. We're making it work. All right, let me just tidy it up a little bit. Okay, so we'll start with the variance. And we'll take the square root later on. All right, so remember, in each case, you go through and subtract the mean, y bar, from each of these elements. And then at the end, we divide by n minus 1. So we'll have minus 3 squared plus 1 squared plus 2 squared plus 3 squared plus minus 3 squared. Yeah, that's right. Okay, then we'll have 9 plus 1 plus 4 plus 9 plus 9. So that's 23/4, which is 5.75, right? And then what we actually need, this means that the variance of y,
Dr.
yes. Oh, is there a mistake in there?
So 9 plus 9 plus 9 is 27 plus 5.
Oh no, what is wrong with me today? You're right. It's so funny how you go through all this is why you want to write down your steps, because you go through all this hard work and then you make a dumb mistake at the end. You don't want to lose all the points. Yes, you see, it always works that way. It's always the stupid little things where you go wrong. All this hard procedure is done correctly. And then and this is what happens. Thank you for catching that.
I do the same thing all the time.
I know, it's so frustrating too. Oh, it's exactly 8. How do you like that? Yeah, so this is why you definitely want to write out all these steps. So I could look at it and say, oops, you were so close right there. Okay. All right, much better. And then the square root of 8 is about 5.6 something. Okay. Hold on 1 second. $5.66 I have. All right. So, oops, sorry. 5.66. Oh, for God's sake. All right. So now we have everything we need to calculate the correlation coefficient. So yeah, way back up there, the covariance turned out to be 0.5. And then the sample standard deviation for X is 14. Oh, no, it isn't. It's 3.81.
I have a question, but I was getting point
Oh.
2.
Oh, wait a minute. No, I hit the wrong button on my calculator. It's 2. Yeah, I knew something was wrong. That looks way too big. The square root of 8 is 2.8. That's better. 2.83. Okay. Okay, that's good. All right. Now, when all the dust finally settles, man, what a pain this problem was. It's 0.046. So basically, the relationship between these two is that it's almost, that correlation coefficient is very close to 0. If you were to draw a scatter plot of these two samples, you would see that there's essentially no connection between them at all. They're just randomly scattered around. There's no pattern to them, let's say. In fact, if you wanted to, no, why not? Let's see what it would actually look like, just because we can. Let's do that. I just feel like it. Hold on a second. This will only take a minute. Now, you obviously don't have to do this on the test. If you were to take these two samples and draw a scatter plot, now there's very little data here, so it's a little tricky to analyze this, but Um, yeah, I mean, they're just sort of, it's a very weird pattern. There's the correlation here is it's really not even a linear relationship. The correlation coefficient really is meant to describe what we call linear relationships. If there's no relationship at all, or if it's not linear, then you're going to get a very low correlation coefficient. Okay, in other words, you could not describe this relationship with a straight line. So that's really what it's telling us. All right, so with all that hard work done, man, at least we're finally finished. Now we can do some probability theory, which is good because these are, conceptually tricky, but they're not nearly as time consuming. All right, anyway, so yes, I see the clock has gotten ahead of us again. It's about quarter after. We've got to have a break after all that. I think you'll agree with that. So let's knock it off for a bit. Now, it's pretty clear to me that we're not going to finish this today. So, and that's okay. We'll finish it tomorrow. And then I'll post what I'll do, I'll tell you what, I'll post this partially completed document on Moodle as soon as we're done so you can look at it. And then the rest tomorrow. And then I'll post the midterm, and let's say you can have about a week or so. Let me look at the old calendar here. Oh man, it's not even January. Our last day is January the 19th. It seems like a long way in the future, doesn't it? Yeah. The 19th right there. And here we're, we're in December. Today's the 30th, right? So you know what? I don't want, well, why don't we do this? Just because we do have some time. If I post it tomorrow, why don't we make it due on, let's say, Monday the 11th? Ooh, but you know what? The problem with that is there's going to be a second midterm and there's a final. All right, I'll tell you what. I'll let you have to the 11th with the understanding that you don't wait till the last minute to do it, because then within a matter of days, the second midterm will be due. And then the final, now since the last day of class is on the 19th, I probably have at least 3 days before I have to hand in the grades. And then the final could be due, for example, on the 22nd. So, all right. This one is fairly time consuming compared to the second and third one. So I'll tell you what, let's make this one due on Monday, the 11th. Does that seem like a stretch? You can hand it in earlier than the 11th. That's fine, but it might take you a while. But just be aware that if you do hand it on the 11th, you're going to need to hand in the second midterm within a few days after that. Let's say maybe the 15th or 16th. And then the final exam will probably have to be done no later than, let's say, the 21st. So we don't want to push our luck. You're okay with it? All right. So we'll just tentatively set down a date of January the 11th for this one, mainly because I know from experience, this is the one that takes the most time. The others might not be any easier, but I don't think they'll suck up as much of your calculation times like this one might. All right, so let's do that. Now, in the meantime, we have to have our break. And also don't forget along the way, there'll be several problem sets that you have to hand in too. So, so far it's been pretty light as far as the assignments go, but that's going to change. And especially after the New Year's Day, there'll be assignments due pretty regularly up until the 19th. So, all right, but I think we're in a good pace here. All right, so let's knock it off for a few minutes. When we get back, we'll dive into question number 4. And this is the stuff we've just been doing, so you'll have no trouble with it whatsoever. Okay? All right, I'll see you in a while. All right, I guess we'll carry on here. So number 4, an experiment consists of flipping a coin 3 times. And we have the following events to find. A is the event that at least one head turns up, and B is the event that at least 2 tails turn up. Okay, so before we do anything else, the most important thing in these cases is to make sure that we've got the entire sample space set up correctly. So one way you can do that is to create one of these so-called binary tree diagrams. And this way it helps us avoid overlooking some of the choices. Now, it turns out you can actually define a formula for this. Let me do that right now before I draw the picture. The number of ways of flipping a coin n times is 2 to the nth power. It's that simple. Actually, yeah, 2 to the nth power. So where n is the number of flips. Okay, so for example, if we flip the coin 3 times, the number of possible outcomes is 2 cubed, which is 8. Now, if you know that, it's much harder for you to not get the sample space set up correctly. Because if you miss one, you'll notice it right away, knowing that there's supposed to be 8 of them. In the past, I've had a lot of cases where people would leave some of them out, and of course, then all their answers are wrong. We don't want that. So at the very least, what we need to know is, can you determine in advance how many elements belong in your sample space? Once you know that, when you start to write them down, if you're missing any of them, you'll notice it right away. The other option is to just draw the tree correctly, and you'll see that you shouldn't miss any of them. So for example, you start out by flipping either a head or a tail. Once you've got your first head, the next flip can either be another head or a tail. If you start out with a tail, your next flip is either either a tail followed by a head, or of course a tail followed by another tail. And then the next flip, if we've already got 2 heads, we can get a third head. We can get a tail. Here we have HT. We can follow that with a head or a tail. And so we do the same thing for all of them. And there they are, 8. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 outcomes listed here. We've covered all the possibilities. Now, the sample space itself can be written in any particular order. I find that this particular order I'm about to write is the easiest to deal with because, well, you'll see in a second, what I'm going to do is start with all the cases where there's 3 heads, and then I'll pick all the ones where there are 2 heads. This one, and this one. It's just easier when you're looking at the events that you're defining to have them organized this way. You don't have to do it like this, but I think it's the easiest way to go. Now, next, what I'll do is I'll pick all the cases where there's exactly 1 head, this one, and this one. So you'll have HTT, THT, TTH, and then finally we have the last case where there's no heads, TTT. So there's 8 of them, 1, 2, 3, 4, 5, 6, 7, 8. Here we have 3 heads, 2 heads, 1 head, and no heads. So now it's going to be very difficult to make any mistakes because the thing is set up correctly and you already know that there's supposed to be 8 outcomes. So A itself, remember, is the probability, or A, it represents the event that there's at least 1 head. Now look how easy this is. At least one head means every possibility except 3 tails. So A is just the first 7 elements in the sample space. So our reward for going through all those steps is that, look how easy this is. A equals HHH, HHT, HTH, THH, HTT, THT, TTH. In other words, the first 7. And because each of these outcomes is equally likely, which, by the way, we know that because a head and a tail are both equally likely to occur, all we have to do is count them. So that's 7/8 or 0.875. Okay, now what about B? For B, we have at least 2 tails. That would be these last 4 cases. Look how easy that is. Okay. So in other words, we're looking for at least 2 tails. Hold on 1 second. I have to find my place again. Here it is. Okay, here's B. So B contains the elements HTT, THT, TTH, and TTT. All right, and again, the reason for that is because it says B is the event that we get at least 2 tails, which means either 2 or 3. Or you can think of it as no heads or 1 head. Either way, it works. Okay, and of course, that being the case, the probability would have to be 4 out of 8, or a half. Or if you want to write it as a decimal, you can put it as 0.5. Now we can work on the more complicated cases. Now, for example, the union. Now, here's what you can do. One option you have here is to say, well, listen, what elements belong to this union? Well, if you look at the way they're defined, you'll notice that between A and B, they cover all the possibilities. So A union B is the entire sample space, which means that the probability, as you know from the axioms, has to be 1. And you're done. Look how easy that was. Man, it doesn't get much simpler than that. Now, another possibility would be to say, well, you know, we could just write them out. You know, it's up to you to decide which way to go. But if instead you had done something like this, would have just said, all right, well, then the probability must be 8 out of 8, which is just 1. And of course, you get the same thing.
I have a quick question, Mr.
Yes,
Ramsey.
okay.
In all cases, is the probability of A union B going to be 1 every single time?
No, it's just if it's been happening, I forgot if this has happened all the time. It's only because they contain all the elements in the sample space. It's just a coincidence. Okay, like suppose we had instead, I'll put this on a separate page. Suppose instead we did something like this. We have the same sample space. And let's say this is our sample space, and I define A to be exactly 1 head, and B is exactly 1 tail. Okay, well then in that case, A would be, it would be these 3 right here. Oh wait, something went wrong here. Here we go. Okay, so then you would have A would be HTT, THT, TTH, and then B would be these three, HHT, HTH, and THH. So then the union of A and B in that case would be HTT, THT, TTH, HHT. They don't overlap. But then the probability would just be 6 out of 8.
Thank you.
Okay. Yeah, if that's been happening in all the examples, it's just a coincidence. All right. So yes, there's a case where we did not get 1. All right. Very good. So for this one, it is 1. Now, what about the intersection? Do they overlap at all? Let's take a look. Let's see if we can show them side by side. Actually, let me just copy them down here. This is A. This is B. So do they have any elements in common? Well, let's see. Why, sure they do. They both have HTT. They both have THT. And they both have TTH. Okay, so the intersection between them is equal to the set containing HTT, THT, and TTH. That, of course, means that the probability must be 3/8. Okay. Whoops. Okay, and that's all you have to do. Now, a complement. Now, for something like this, what you could actually do is create the set that contains the elements A complement. In other words, we know that this is A. What elements belong to A complement? Basically, whatever's left over, whatever is not included in A, that's A complement. In other words, A contains all the elements except TTT, which implies that A complement is just 3 tals, which in turn implies that the probability of this happening, again, given that they're all equally likely, is 1 out of 8. The other option here is to say, all right, well, you know what? Based on our complement rule, look how easy this is. It's the same thing. Of course it is. Yes. It's just 1 minus the probability of A. Okay, so you can use whichever approach makes sense to you. Whichever one is quicker and easier, you can go ahead and do that. With B, for example, what I'm going to do is define B complement by looking at B. B is right here. And we can get rid of these underscores. So therefore, B complement would simply be what's left over, anything that's missing from here that is in the original sample space, HHH, HHT, HTH, and THH. Therefore, because it also contains 4 elements, the probability of B complement will be 4 out of 8. Okay, 4 out of 8. The other option is to say, well, you know what? The probability of B complement equals 1 minus the probability of B, which is 1 minus 4/8, which is 4/8 or a half. Either way, you'll end up with the same result. Okay. Now, oh boy, here our favorites, the conditional probabilities. Now, remember how these are defined. Now, just a few minutes ago, we saw that this probability is 3/8, and we saw that the probability of B was 4/8. Now here's a little algebraic trick you might remember. This is the same thing as 3/8 times 8/4. So in other words, instead of dividing by 4/8, I'm multiplying by the inverse, which is 8/4. These cancel out, and I'm left with 3/4. Or of course, 0.75. Now, how about B given A? Well, this one is the probability of A and B divided by the probability of A at this time. Remember, this event is the one that goes in the denominator. So you've got 3/8. Now remember, way back in the beginning, A had a probability of 7/8. That's 3 out of 7. I believe that's about 42%. Let me just double check that. 3 out of 7 is approximately 42.9%, let's say. Either one is fine. All right, now we have some conceptual questions down here. Are A and B mutually exclusive? Why or why not? The answer is no, and there's a couple of ways, or at least 3 ways we can express this. Number one, you can say A intersect B equals, let's see, what did they have in common? It was up here somewhere. Here it is. Let's use this, which does not equal the empty set. Okay, in other words, their intersection is not empty. The other way of writing it is that the probability of A and B, which we already know is 3/8, is not 0. So again, or, now keep in mind, you don't need all of these. I'll just put in a little or here. And then the last one, you can do this in English by simply saying the intersection of A and B, or actually what I'll do is call it, put it this way, A and B have at least one element in common. That will also be sufficient to prove that they're not mutually exclusive. And you can pick whichever one you want. Beautiful. Now, are they independent? Why or why not? Well, independence, remember, implies that A given B equals A, and B given A is B. Is that true here? Well, we just proved a few minutes ago that the probability of A given B is 3/4, or 7.75, and that we know that PA is 7/8, which is 0.875. So already you can see the first condition was violated. So since this condition fails to hold, this is sufficient to prove that A and B are not independent. You do not have to bother checking the second condition. The first one is false, and that means no. Okay. All right, now how about this one, complements? Now remember what it means. In order for A and B Two conditions must be true. Okay, their intersection must be empty. All right, let me just grab this. And their union here we go, is the entire sample space. Now, you can also, oh, you know what I just realized? I wrote 0 here. This is, sorry, this is the empty set. Or the alternative way to express this is to say, you know, this first probability must be 0. And the second probability has to be 1. Now, that second condition actually is true, as you saw. So we're going to say that since this probability is 3/8, which again does not equal 0, this means that A and B are not complements. And I'll put in parentheses, even though the second condition is true, it doesn't matter. It has to be both. So if you're determined to do this in English, you could write the following. A and B are not complements because they are not mutually exclusive. Okay. So you can see there's usually multiple ways of explaining the same thing. All right, now, what does that leave us with? We got more probability here, 5. Okay, what's going on here? Oh, sometimes it gets like this. All right, but anyway, we have 5, 6, and 7 to go. We'll do this tomorrow, and then we'll get back into chapter 6. In the meantime, don't forget, tomorrow you're supposed to hand in chapter 3 and chapter 5 problem sets, and then you'll have roughly a week and a half to get those first midterm done. Okay, so what I'm going to do is post just this part, and then tomorrow I'll fill in the rest, of course, and that way you'll have plenty to study from as you work on the first midterm. Okay, so are we all set? Are there any last minute questions? Okay, good. Well, then I'll see you all tomorrow.
Have a good
And
one.
if I forget the invitation again, I won't. I'll send it out right now. But sometimes, you know, like if I do forget, obviously when I sit down in front of the computer, I'll realize it and I'll send it to you right then and there. But for the most part, I'm going to try very hard to send it to you the day before. If not, well, it means I just forgot. You can send me an email and say, listen, where's my invitation? And then I'll send it to you. But I'll try not to let that happen again. All right. So I'll see you all tomorrow then.
Have a good one.
All right. Bye. See you later. Yeah, the first due tomorrow, right? Tomorrow night, basically, midnight-ish. Yes, because that's our last meeting of the week. And then we have a holiday.